In this lesson, we explore logarithms and introduce logarithms. So this is a video that was made a while ago. Unfortunately, the sound didn't work for the first part, so I'm going to try to add some sound here as we go. So if the sound seems a little bit funny, that would be why. So first I want you to look at the graph of y equals 2 to the x. I want you to consider what that looks like. You can see it here on the screen. Hopefully you can convince yourself that this is in fact correct. And what I'd like you to do is to consider some of the characteristics of this graph. You can pause the video now and do that, or you can sit back and enjoy. So it's a function. Obviously, it passes the vertical line test. For every input, there's only one output. It's a function that's increasing. It does have a horizontal asymptote, and a horizontal asymptote is there at 0, as you can see. So again, here's just writing out some of the characteristics of this function. And I want you to think about these characteristics because pretty soon I'm going to get you to think about the characteristics of the inverse of this function. So you might want to be thinking about that as you go along. So we mentioned the horizontal asymptote at 0. The graph will approach 0 as x gets closer to negative infinity, but we'll never actually touch it. Think a little bit about what that might mean in terms of the inverse of this function and what that might mean. As you may remember, the inverse involves switching the x and the y values or doing a reflection in the line y equals x. So what about the domain of this function? You've looked at this function in grade 11. You can probably guess what the domain is going to be. Yep, and there it is there. The x values can take on any value. There are no restrictions on x when we put a variable in the exponent, so we get that x is an element of the reals, and that's the domain. And what about the range? Look at the graph, think about the range. So again, the range of the possible y values. If you look at this graph, you can see that y can get infinitely big, but that y can never be less than or equal to 0. So the range is that y is an element of the reals, such that y has to be strictly greater than 0. So it can't be equal to 0, it has to be greater than 0. So these are the characteristics of the graph of y equals 2 to the x. Think about what the graph of the inverse function is going to look like. You may want to sketch both the graph itself of y equals 2 to the x and the inverse. Think about how some of the characteristics that we've listed here will be different for the inverse, and try to convince yourself of what that graph is going to be like. Again, the graph of the inverse is a reflection in the line y equals x. So we could draw the line y equals x on the grid. When x is 1, y is 1. When x is 2, y is 2. When x is negative 1, y is negative 1, and so on. So we can do that and then sketch the inverse. In green here, you can see what happens if we look at y equals 1/2 to the x. So that's just changing the base. It's important to realize that the graph of y equals 2 to the x does show a graph that's increasing or a function that's increasing, but we can also show a function that's decreasing so long as the base is a fractional value between 0 and 1. So hopefully you have the graph and its inverse. There are a couple different things, suggestions about what the inverse might look like. Probably helpful, again, as I mentioned, to draw the line y equals x. That one actually doesn't look half bad. And the one that was just drawn might be a good inverse for, um, oh no, that wouldn't be a good inverse, never mind. Not sure what that was there for. Alright, so here it is, the line y equals x, approximately. Would have been better with a ruler or a straight line. Remember, to graph the inverse, we're going to swap the x and the y values. So at the point 0, 1, the y-intercept, we're going to switch x and y. So x becomes 1, y becomes 0, and we can do that for a few other points. So here's the point 0, 1. When we reflect that in the line y equals x, the x and the y values change. And we get the point 1, 0. Again, we could do that for a couple other points if we wanted to make sure. Here's the point 1, 2. If we switch x and y, the coordinates become 2, 1. We can plot that point, and we can continue on like this and see what's going to happen. Now remember here that if we're swapping the x and the y values, the horizontal asymptote is actually going to become a vertical asymptote. Just to show you that we can also do this on the negative side of the y-axis. Here's the point negative 1 and 1/2. So negative 1 comma 1/2. Swap the x and the y values. We get 1/2 comma negative 1. And you can see that point right there. So you can see this curve starting to take shape. Looks something like this. Kind of missed some of the points there, but I think you get the idea. Try that one more time. It's not too much better, but at least it's going through a couple of the points. So there's the graph of y equals, that's the graph of the inverse function. We haven't talked about what that notation looks like yet, but we'll make sure that we do that here at some point. You should be able to see the characteristics of this graph. So talk about the same kinds of things that we did for the original graph. Is it increasing? Is it decreasing? What's the domain? What's the range? Maybe intercepts, kind of important too. So notice that the y-intercept became the x-intercept. And the x-axis, which was an asymptote, that asymptote that was on the x-axis became an asymptote on the y-axis. Little interlude here. Sorry, we had some technical difficulties, and very shortly I think we're going to get the sound back. So once the sound from the video comes back, I'll tune out and let you listen to the rest here. All right, back to the graph here. See if you can come up with the characteristics of this inverse function. Should probably cut this part of the video out, but that might take a little bit of time. So this is a just going through and changing or listing the characteristics of the inverse function. All right, hopefully you had a chance to go through some of these. We're going to see some here, and I'm guessing that in a minute or so you'll have the original audio from this recording to follow along with. So if you look at the graph here, you can see that in fact the green green curve, pardon me, is still increasing. So the original function was increasing, the inverse is also increasing. This one has a vertical asymptote. That vertical asymptote is at x equals 0. And you can see that the graph gets closer to, but never touches the y-axis. The domain here, if you look at all possible x values, you can see that x is never less than 0. In fact, it's always greater than 0, so it's never equal to 0 either. So the domain is just that x is an element of the reals such that x is strictly greater than 0. And the range, well, y can be anything. It can be infinitely small and infinitely large, so y is an element of the real. So you can see here that the range and the domain really just ended up switching as we did that inverse.
Here we go. How's that? I think that's probably better. I just noticed that I don't think I turned this. The range here. What about the range? Yeah. Not x, but y. Awesome. Sorry, Owen. Didn't mean to leave you not hearing for a while. So we've got the range here. Y is an element of the reals. Anything else? Yeah, let's do that. Let's talk about that. So it has an x-intercept at, it was 1, right? And this one over here had a y-intercept of 1. Obviously, we did the sort of swapping the x and the y values, so our x-intercept becomes our y-intercept, and so on. Algebraically, if we do what we just did graphically, it kind of looks like this. So the function, the equation over here is y equals 2 to the x. The equation over here would be to swap x and y. Typically, if you find the inverse, what you do is you swap x and y, and then you solve for y. So this really becomes, the equation here becomes x equals 2 to the y. All I did is I swapped x and y. Graphically, it kind of made sense. Are you okay with that? Okay. Graphically, it kind of made sense. As an equation, this is what it looks like. And typically, we would solve this. You know, if I gave you a linear function and asked you to find the inverse, we would solve this by isolating y and getting y all by itself. That's kind of where we're headed in the next couple of days. For now, I guess I should introduce this, what's called a logarithmic notation. And basically, the inverse of y equals 2 to the x is this. And if we were to actually express this with this sort of log notation, I know that you guys have seen logs before, we get something like this. Yes. Yes, so there's a log button on your calculator that that says log. But I wrote an A here. There should be a 2. I was just writing the general form. Just a little 2. It's a subscript. So the way that you read this, no. So it's kind of like the log and the x are on the same line. Sorry, Aaron. Yeah. And the 2 is a subscript. So the way that you read this is that this says here that this here is going to be the base of your exponential form. This will be the exponent. And this is going to be the result. So what this notation, and I know that this is new to you, this particular notation. It's going to take a little bit of time to kind of get comfortable with it. But what this notation means, in a way that you're used to dealing with, is it means that if we take 2 and raise it to the exponent y, we're going to get x. Well, that's just what we had right here. So 2 to the y is equal to x. Just a different way to write it. So this is called a logarithmic function. I mean, the whole thing is, but
Why would you write it like that?
yeah. I wanted to show you the connection between the log form and this form right here. Ultimately today, what you should be able to do is I should be able to give you something like this, log, let's say 327, and you're going to tell me what that equals, kind of thing. So I want you to get used to the idea of seeing that this is just another way, this logarithm is another way to write exponents and exponentials, except now we're solving for the exponent instead of trying to come up with the result that we had here. So this is logarithmic form or notation. Is that okay so far? I want to do some examples so you can kind of get used to this. No. This, I mean, I could have made this your homework last night. I'm not sure why I didn't, but so here's a sample here of an equation written in exponential form. This is a form that you've seen before. Might not be your favorite form of an equation, but it's one that you've seen before. If we write it in logarithmic form, remember the base goes here as your subscript, the exponent is over here, and the result of the base to that exponent goes here. In grade 11, you spend some time solving equations like this one. Anybody remember how to do that? We're going to do it later on, but you could do log of something, but there's even an easier way. Guess and check, yeah. You're laughing, but that's how you do it in grade 11. You do it in grade 11 by guess and check, or you do it in grade 11 by saying, hey, is there a way that I could write this 8 as 2 to the something? Because if I can write this as 2 to the something equals 2 to the y, then y must be equal to that something. So 2 times 2 is 4 times 2. Here's where that kind of guess and check comes in. 2 cubed would equal 8, so that means that y would equal 3. Is everybody okay with that? Yeah. I don't think it's a bad thing to write down. I think that would be a good idea. So again, same sort of thing here. 2 to what exponent would give us 8 is really what this is saying. This is another way to write this, but having it written a different way. So 2 to what exponent would give us 8? Well, that means that y here would have to equal 3. Same reason that we had over on the left there. Is that okay? Awesome. So that's logarithmic form. I don't think I need to say actually very much more. We've kind of looked at the graph of y equals 2 to the x. I should mention right away that although there is a log button on your calculator, it's not going to be very helpful to us for at least a little while. The trouble with your calculator is that this is what we call a log. So the way I should mention, the way that we read this, by the way, is log 8 base 2. I might write that down actually. So log 8 base 2 is how you read that. I know it's tempting to say log 2 8, because we're so used to reading from left to right, but the way that we read this is log 8 base 2. The trouble with your calculator is that you'll notice that your calculator doesn't have a little base button. All of the work that your calculator will do with logarithms is all in base 10. Base 10 is the counting system that we know. You know, you count from 0 to 9, and then you add 1 to the next place value over and add some zeros. Anyway, your calculator is only capable of doing base 10. All that means is that at some point we just have to make sure that we're doing our work in base 10. But for now, we need to make sure that we're comfortable kind of working in the different bases. So your calculator will come in handy, not just yet though. We looked at the graph of y equals 2 to the x. Let's consider now the graph of y equals a to the x. And I guess what I want you to consider is what happens if a is greater than 1, let's say. What does this graph look like if a is bigger than 1? So for example, a is 2 or 3 or 4 or 5. It's going to increase, right? So for y equals a to the x, if a is bigger than 1, we kind of did that way back over here. A was 2 here. What happens if a is 3? How's the graph going to be different if it's y equals 3 to the x? Or y equals 4 to the x. Yeah, it's going to increase faster. So y equals 3 to the x. Notice here, it's not a coincidence, by the way, that at x equals 1, the y value here was 2. Remember the equation was y equals 2 to the x? You plug a 1 in here for x, you're going to get 2. So if we make the base 3, then we kind of get something that looks like this. And so on. So as a increases, the curve gets steeper and steeper. And in fact, we kind of get the opposite behavior down here, but I'll kind of leave that for you to kind of figure out why. What if I should write that down, I guess, because if a is greater than 1, the graph increases. We've kind of talked about that already, but it increases more. How do I write this? The graph increases as a increases faster as a gets bigger. The graph increases faster as a gets bigger. Now, what happens if a is between 0 and 1? So, for instance, y equals 1/2 to the x. Sure, the graph's going to look like this instead. Yeah, it was like this before. So if a is 1/2, we get a graph that looks like this. What's going to happen if a is 1/4? Well, let's have a look. If a is 1/4, so if we're looking at y equals 1/4 to the x, let's just look over here. What happens when a is -1? Sorry, not a, x. We get 1/4 to the -1. Where do we go with this? Aaron's going to have a hard time with this. I don't think you did negative exponents, did you? Last year? That's why. But the rest of you should be okay. Remember that when you have negative exponents, you can, well, first of all, I guess that each of that exponent applies to both the numerator and the denominator. In order to make the whole power here positive, we just move the, Emmy's got the sound effects today. We move the power from the numerator to the denominator. So really we get 4 to the 1 over 1 to the 1, which is equal to 4. So when x is -1, y is going to be 4. Somewhere way up here, And how is the graph of y equals 1? What's this graph going to be at -1? 2, right? So again, we kind of get this behavior that's really steep over here, and probably we'll kind of do something like that. Well, this is 2 to the x. And this one here is y equals, sorry, this is a half. Thanks for asking, Jenna. Let's try that again. This is y equals 1/2 to the x. And this blue one here is y equals 1/4 to the x. Whoa. So it's steeper over here, and you kind of get this. I mean, it's the same sort of thing that we saw with. Oh, I didn't do it on there. Anyway, with the other one. I think with that information, you could probably look at what happens to the graph of the logs as you change the base as well. I mean, it's just a reflection in that line y equals x. So you can kind of use the exponential to help you graph the logarithm. This is like the introduction to logs. Any questions so far? You won't need that much of a lesson. It'll be. We probably won't do too much with negative exponents, so I think you'll be okay. The other thing that I want to talk about today, just very quickly, because we've done this a whole bunch already. Transformers, yeah, or transformations. Funny one, I guess. I'm going to do this in base 10, and I know that I was using a for the base before. I'm going to put the a out front here because that's how we do it for every other single type of function. So, but the same idea here of looking at different bases, all of these things will apply just the same. It is. A is the vertical stretch or compression. So this should look very familiar to you. I feel like we've kind of done it to death. The transformations, remember that A is a vertical stretch or compression. Yep. So everything that we've talked about before about these graphs applies here, which is why we're kind of blasting through this fairly quickly. And as Cam said, we get a reflection in the x-axis here as well. K does a horizontal stretch or compression. And a reflection in the y-axis. D was a shift left or right, opposite to the sign in the brackets. And C was a shift up or down. I don't think it's worthwhile for me to go through and do some examples here. I think you guys are pretty good at this type of thing. So here's what I would like you to do for work today. So work from 2 different pages today, 451. Question number 1, we'll just do A and C from 1. Question 2, then you can do 4 to 7, and then 9 to 11. There's about half an hour left. My guess is that you'll be able to get that first chunk done before you go. There's not a lot of work there. Question 4, just do every other one, 1, 3, and 5. 5, you can just do A, C, and E. And question 8. It looks like a lot, but if I just wrote 1 to 11, For each of them, it would actually be more. Hey, thanks. All right, so first page done before you go. Yeah, that's right. Yeah. Just for 4. Yeah, just for 4. Do questions 1, 2, or 1, 3, and 5. Oh, how's it disabled? Sorry, Owen, I was just going to see if I can get you to ask some questions, but it doesn't look like I can. No, I was talking to Owen.
Oh, okay. Can I go my last piece of paper?
Yeah, sure. Owen, if you have any questions, just fire them off to Cam, and we'll try to get this question thing sorted out.